thanks very much for everyone for coming along today. We've got a very special guest all the way from Taiwan. But before I introduce her, I'd like to acknowledge that we are gathered on the lands of the Wurundjeri people. My respects to the elders, past and present, and extend those respects to any Indigenous peoples here today. We acknowledge that the Indigenous peoples have always been making discoveries and sharing knowledge. And we are really privileged to keep on that legacy. And as we hear from more discoveries today from Professor Chun-Chuan Chen. So I first met Professor Chen back at UCL. So we were doing our PhDs at the same time. So it's been about 20 years, and I'm so delighted that she's here today to present her work. And even though she's referred to as Professor Chen, for me, she's still CC. So that's what so we'll go with CC. Professor Chen obtained her PhD in computational neuroscience from National Yang Ming University in 2009, with her research training being done at the Wellcome Trust Center for Neuroimaging at University College London, where we met. She has held academic positions at several major Taiwanese institutions and is currently a professor in the Department of Biomedical Sciences and Engineering at National Central University in Taiwan. Her work spans neural engineering, precision medicine, and the application of AI and virtual reality in neuroimaging and brain-computer interface research. Professor Chen is internationally recognized for her contributions to MEG signal processing and EEG as well, and the development of novel VR-based neurocognitive assessment tools for disorders like ADHD, autism, and substance use disorders. Her recent publications focus on integrating neurophysiological data with machine learning and improve clinical screening and rehabilitation strategies. So without further ado, CC, please take the floor. Thank you.
Nice introduction, and it's really a great honor to be here today. And I'm really very happy to see Marta again, and also I am very happy to have this chance to maybe later to have a look of the famous OPM. And today I'm going to present my recent work on bridging digital health technologies and neuroengineering with a focus on translating research into clinical application. So the title is Digital Health and Neuroengineering from Bench to Bedside. And please bear with my accent because I just realized people don't, when I go to the restaurant and order my meal, they don't understand me very often. And if you have any question, I will be happy to address your question at the end of this presentation. And I will start by talk about the key concepts of digital health and neuroengineering, and then I will introduce the core technologies that will be used in DH and neuroengineering. Moving forward, I will use DH and NE for digital health and neuroengineering. And then I will show you some examples how I make this happen. How can I translate our research into clinical practice? I will use, I think I probably don't have much time today, so I will just talk about ADHD in details, but I will show you some other examples, some other applications. So first, the definition of digital health according to FDA. Digital health are systems that use computing platforms, connectivity, software, and or sensors for health care and related uses. And digital therapeutics is a kind of digital health. And the basic concept about the digital health, the digital therapeutics is to deliver evidence-based therapeutic interventions to patients, and in order to prevent or manage or to treat a medical disorder or disease. And as you can see from the figure on the left-hand side, so this is the first FDA approved digital prescription for digital health, and from the right-hand side, it shows the expected market for digital health. You can see that it is expected to grow dramatically, actually, and this growth underscores the increasing significance of digital health as a fundamental component of future healthcare system. And neuroengineering is an engineering discipline focused on understanding, repairing, and enhancing neural systems. A core principle is to consider the brain as a controllable machine, wherein we aim to predict outcomes based on specific inputs or perturbation. One example is the use of brain-computer interfaces for motor rehabilitation in stroke patients with motor deficit. So in this case, motor rehabilitation, biofeedback is provided to the subjects for adjusting their performance, and while accurately predicting the degree of improvement after this rehabilitation remains challenging, because the improvement varies dramatically across different subjects. However, patients always experience functional gain after this rehabilitation, and this is attributed to the underlying change in the brain, which is neuroplasticity, and that's why we have to combine NE with DH such that we can predict our outcome. So in order to achieve neuroengineering, we have to answer 3 questions before we can conduct this kind of study. The first one is where in the brain to target, and the second is how to rewire the connections, and finally, what tools to use. There are a lot of tools can help to achieve this kind of goal. For example, you can do it physically. So you can use physical training, or you can use TMS. And maybe in our case, we use virtual reality interventions. So in my application, 4 core technologies are used for this purpose. The first one is virtual reality or augmented reality. We use these tools to create controlled and immersive virtual environment to mimic the real world without any risks. And especially we can use VR as a tool to design a specific or different cognitive task. We will see that in our example of ADHD. And the benefits of VR include standardized stimuli, dynamic and immersive tasks, and the ability to trigger and monitor brain and behavioral responses in real time. And then the second technology we used is wearable sensors or smartphone. They can provide real-time measurement of neurophysiological data like EEG, EKG, and or skin contactance. And the most important thing is that they can enable the home-based patient monitoring and support long-term health tracking because they are not that expensive. You can probably buy it and use it at home. And the third technology is artificial intelligence and machine learning. They can extract unseen patterns from the data and offering speed and accuracy. And the fourth one is Internet of Medical Things, IoT. In connect health, the IoT connects health devices into a secure and unified network. This is very important if the data amount is huge, and which is our case. So why is AI necessary? Because it's very popular now. Everybody does it, so we have to follow it. From my perspective, maybe no. It's because when we conduct biomedical studies, particularly in neuroscience, we often encounter a major challenge of big data, right? So the data is typically heterogeneous. For example, we can have a variety of data like EEG, EKG, and behavior data as well. And also, the data can change with time. So it evolving relationships among data, and of course the data is complex because they may have nonlinear behaviors between parameters and even between data models, data modes. And also it could be autonomous. It could have autonomous sources with distributed and decentralized control. This characteristic is not a typical pattern for our data because this refers more like you get the data online. So people from all over the world can answer your question and give you the data like this. But nevertheless, this set of characteristics is known as the hack theory. And because the data is so huge, so it can lead to difficulties in exploring the data and also potential biases in interpreting it. Like imagine that we have a data like the elephant, and we are blind. We try to figure out what the data is like, but if we just because we are blind, so if we just touch the tail, then we say, oh, the elephant is like a thin stick, and if we found the parts of body, and then we say, oh, the data is like a pen or something like this. So it's always our big worries because the data is unstructured. Therefore, we have to use, we have to we have to use machine learning because biomedical data are rich and complex, and it's too large and multi-dimensional for traditional methods like univariate hypothesis testing. But by saying this, I didn't mean that we give up on hypothesis test totally. No, we have to work. I would suggest we use both the statistic test and also the AI. And on the other side, machine learning is grounded in statistics. They can go beyond traditional methods and help us to navigate and interpret the complex and high dimensional nature of our data. So in the past, those the AI models are inspired by our brain itself. So it used AI used to have this artificial neural network. They just try to mimic how our brain works, and then, but it evolved dramatically nowadays. Recently, we can see the version of generative AI. So from a mathematical perspective, traditional machine learning typically maps many to a few outcomes, while now the generative AI, they can map the opposite. So they can use only a few inputs and then project them to many possible outcomes. So why has AI achieved so much attention recently? I would say it started with this paper published in 2012. The title of this paper is Building High-Level Features Use Large-Scale Unsupervised Learning. Have any of you heard of this paper? So in a team at Google built a very deep neural network to answer a question: how do millions of people do on YouTube? What do you do with YouTube? And this team fed the network 10 million digital images captured from YouTube randomly, and then allow the system to run automatically from the data without any labels. So it's, as it said in the title, it's a unsupervised learning. And then basically it's just like they let the data speak for itself. And then what did the network learn? At the end, the system discovered that people were mostly looking for cats. And in the same year, there's an article published in New York Times titled "How Many Computers to Identify a Cat?" 16,000. It sounds ironic, right? Ironically, a little bit. But in that article in New York Times, it explains how deep learning works by using facial recognition as an example. So basically, in deep learning network, they start with let me refresh, sorry. So deep learning relies on multiple layers of increasing complex representation to classify patterns and shapes, starting from simple edges to full objects like faces. And just like the figure shows, so first they have one layer to detect the luminous, and then for the second layer, they have this layer is used to detect the edge or shapes, and then finally, the third layer can capture some pattern, complex patterns of this image. Finally, they can recognize a face. But to me, actually, it's there's a biological correspondence to this hierarchy. So in the retina, we have photoreceptors of cone or rays, right? They can detect the luminous, and then this information is transmitted to primary visual cortex. So in V1, primary visual cortex, we have simple and complex cells to detect the edges or the changes. Then the information can be transferred further to fusiform face area, so we can extract some patterns of face. Then finally, maybe, but this it's just my point of view. So maybe this information is transmitted through like a ventral stream or dorsal stream to give you the idea about this figure. So that's the structure of deep learning. But however, deep learning initially didn't gain widespread attention, and largely because only a computer, like a company, sorry, because only Google can afford a study of this big scale, 16,000 computers, right? But then I have to say that after the achievement of AlphaGo, AI has received so much attention. Do you know AlphaGo? So, yes, Go game actually. So in 2016, AlphaGo software, an AI software developed by DeepMind, a company, and defeat AlphaGo defeated Go world champion. Basically, it demonstrates the incredible power of AI. And this group also published 2 master papers in Nature. And Demis Hassabis, he is the founder of DeepMind, the company. After this achievement, he sold this company to Google. So now it's Google DeepMind, and he is the CEO. And so then last year, this group launched the AI software called AlphaFold, which make a major breakthrough in protein structure prediction. So he was awarded a Nobel Prize in chemistry. And I took the photo of him from his Nobel Prize lecture. Judged by the photos, we can, from the previous and now, we can tell what caused him to achieve, to get a Nobel Prize, right? A suit from Savile Row. So what exactly, as we said earlier, what exactly machine learned from our brain? So let's begin with the activation of neuron. Maybe I can, okay. I guess, do you know the mechanism for action potential on a single neuron basis, right? So this neuron, maybe can I sit down so it would be easier for me to control the computer? So the dendrites of a neuron can receive chemical signals from other neurons through synapse, right? And then this incoming signal can be either excitatory or inhibitory, and they are integrated at the soma, right? And then if the combined potential at the axon hillock reaches a certain threshold, then an action potential will be triggered. Otherwise, the signal ceases here. So we have a checkpoint here, at the hillock. And this is actually the principal forms the foundation of neural network. So in neural network, we consider nodes as neurons. So on the left-hand side, the input corresponds to the signal received by received at the synapse, and the weighting represents the characteristic of those inputs, could be positive or negative, and how strong those signal can affect this neuron. So basically, the weight represents the strength and the polarity of the incoming signals. And finally, the action activation, okay? Oh, finally, activation function in a node is applied to mimic the thresholding at the axon hillock. So basically, in this way, we have weighting to weight the importance of the input. And this is a neuron. So we received many inputs, and then we weight them. Then if there is something that cannot be explained by this model, then we put it as bias. So at the cell body, we have this formula, we have this integrated potential, and finally, we can use activation function to adjust whether this information is going on to the next or just stop here. So that's the foundation of neural network. And we can actually extend this structure. So I will introduce two example networks, and I will just briefly go through it, but I will not cover all the details. The first is MLP, multi-layer perception model. So in this model, this MLP, we have one input layer and one output layer. One input layer and one output layer, and one or many hidden layers in between. And during the training of this model, we basically adjust the weighting such that we can get a derived outcome. And the next one I'm going to talk about is convolutional neural network, CNN. So because in MLP model, we don't take into account the spatial relationship between nodes, right? It's only a feed-forward fashion. It's only in a feed-forward fashion, and with no lateral or recurrent connections. So, however, we knew that biological neural network is a big, extensive lateral interactions which contribute to content-dependent processing. So in this case, in order to take into account lateral or recurrent connections, we have this CNN. And in CNN, we use two-dimensional convolutional kernels to incorporate local spatial dependencies between nodes. And this can effectively capture the lateral relationship within structured data, such as images. So when you use CNN, you must be sure that your image, your input data is structured. So because you have to take into account the spatial relationship, so you must be sure that they are related to each other. And after seeing the two examples, you might have this feeling that many deep learning models can be understood as simplified abstractions of biological networks, right? Now, let me show you some examples of DH and E. The first one is about objectively detecting of ADHD. And in this case, we developed a system called Intelligent VR Classroom System. Let me talk about the ADHD a bit. So ADHD, attention deficit hyperactivity disorder, is a kind of neurodevelopmental disorder. It it affects like it affects like 7.2% of children aged from 6 to 18 worldwide, and in Taiwan, ADHD diagnoses are increasing common. And children with ADHD often inhibit inattention, impulsiveness, and hyperactivity, which in turn affect their academic performance and social interaction. Although it's well known that early diagnosis and treatment can significantly improve the outcome of ADHD. However, the current diagnostic method, always based on DSM-5, is time-consuming, and it relies on relatively subjective interviews with parents, teachers, and clinicians. Very often, we observe that this diagnosis can actually cause divorce because the physician, the doctor, has to interview with the parents, and the mother is very supportive. So the mother said, "No, my son is not ADHD," but the father may say, "Oh no, the father may be very impatient," and he said, my son is definitely ADHD kid. So because, and this is all because of these interviews. So if there is a way to objectively scan the probability of ADHD, so this is actually our goal. So we wanted to develop an intelligent VR classroom that supports more efficient and objective ADHD diagnosis. And the second thing about ADHD is the treatment. ADHD is typically managed through behavioral therapy, medication, or both. And the behavioral therapy aims to help children develop positive behavior and reduce problematic behaviors, often involving parents, teachers, and therapists. And common approaches include parent training, classroom intervention, and cognitive behavioral therapy. However, treatment efficacy varies significantly due to many factors, such as the time, the effort the patient and parents put in, and the individual needs. So our system addresses this by offering individualized training through adaptive training strategy and track progress to enhance the therapeutic outcomes. So in our system, we take the advantages of modern techniques, including VR, wearable devices, AI, and OMT, as I addressed previously. And we developed an intelligent VR classroom to enable the precision medicine for ADHD. This is the prototype of our latest product. It looks like an ordinary VR headset, but we see embedded in this system, we have several wearable sensors. Here you may see the EEG and the sensor for tracking the eye movement, and also the sensor to sense the head movement. And then the scenario within this VR classroom, it's actually a modified go-no-go task. So subjects are instructed to continuously look at the whiteboard directly in front, and different digits randomly appeared on the whiteboard with an interstimulus interval of 2 seconds. And they were instructed to press a button when they saw 0 after 1. And this is the 0 after 1%, 0, then this is the go condition. And then if they saw something else, then after 1, then they remain still. And in total, 75% of total trials are go trials, while the remaining 25% are no-go trials. And so this basically, you basically can recognize this typical go-no-go task, right? But unlike the traditional version, we occasionally introduce task irrelevant visual and audio distraction, such as the siren of a fire truck passed by the window, or a classmate yawn from time to time, something like that. And this is because the traditional go-no-go task was mostly given to subjects in a well-controlled laboratory setting. So it's hardly considered the effect of unexpected distraction like occurred regularly in our daily life. And from the therapeutic perspective, it's very important to study the impact of distractions, as children with ADHD are more easily distracted and by distraction, and a better understanding of the mechanism underlying distraction suppression will help the design of behavioral treatment for ADHD. And during this task, we record a variety of neurophysiological data, including head movement, eye movement, EEG, alongside with the task performance. Now let me show you how this system works. I'm playing this.
The virtual classroom game uses an all-in-one VR headset and its interactive controller. Wearing the headset, users can walk around freely without space limitation. The headset supports eye movement tracking function. And relying on this function, we can also implement EEG data integration. When wearing the headset, the first step is to rotate the strap up, and place the lens close to the eyes. Then rotate the strap down over the head. At last, adjust the strap and turn the strap dial clockwise to tighten the VR headset in a comfortable position. Users can play the game once the hardware has been worn. After starting the game, users need to configure the game task first. After the game begins, the user will sit in a classroom. The game rules are slightly different depending on different tasks. Take CPT test for example. When playing the game, there is a series of letters appearing on
This shows what the subjects see within when they wear the VR headset, but without those data in this application. For those we used to with biofeedback, then the subject will see those data in real-time fashion.
one at a time. Users need to pull the trigger button when the letter A is followed by the letter X. During the game, the user's eye movement data, head movement data, and EEG data can be captured in real time. In the game interface, there are two dynamic cylinders on the left and right side, to respectively display the user's real-time focus degree and relaxation degree. The bubble in the screen can locate the user.
The relaxation degree and the focus degree is provided by the manufacturer of EEG company. So actually we don't know what's that. We don't use it.
Point position in real time. After the game, the user's cognitive function evaluation report can be checked. The report is divided into 4 modules as task performance, group performance, data characteristics, and the AI results for ADHD diagnosis and assessment. The task performance data and historical performance data charts of this test can be viewed in task performance module. The percentage of the user's data in the group can be viewed in group performance module. The data characteristics module can display the feature points of eye movement data and EEG data extracted by data analysis. Last but not the least, using AI evaluation technology to analysis and evaluate the user's ADHD tendency.
So in this study, we recruit 32 typical developmental children and 49 children with ADHD. And after the subjects complete the task, the data was analyzed using both traditional statistic methods and this AI machinery. First, we perform the pre-processing as usual, and then to remove and reduce the artifact, then we transform the data into different representation if it's necessary, such as high frequency representation or connectivities. And of course, you can use the raw data directly, depending on your hypothesis or the trial. And then you have to choose the AI model based on your belief or experience. Then we have to train. We split the data into training and the testing subsets and validate the trained data, trained model using cross validation. And finally, we can get the appropriate metrics to report the outcome of our AI results, including like accuracy or sensitivity or specificity. So now let's have a look at the data. first we have to validate whether this VR-based go-no-go task can elicit the typical activity. So first we examine the trials without any distraction. So we found that in the frontal area, the N2 is stronger in no-go task, and the P3 is greater in no-go task as well. While the P3 component in HPD, the go task actually has a greater P3 peak. So this confirms that this VR system can elicit typical go-no-go task responses, and confirm the efficacy of our experimental paradigm using VR. Then we examine the group specific effects of trials with and without distraction, because distraction is actually the key point of this system. And in the TT group, we found that there's only one thing significant, which is the N2 latency in no-go task. And so for the group one, it's the one with distraction, and the orange one is the no without distraction. And in the ADHD group, the D trials was associated with a significant reduced in P3 amplitude, as well as significant prolonged latency in P3 components during Go trials, and in N2 during both Go and no-Go trials. You can see here. For ADHD group, we basically get a significant reduction of P3 peaks, and also significantly prolonged latency in Go and no-Go condition. Regarding the oscillation, both groups exhibit similar pattern in Go trial. So we can find decreased alpha power in D trial compared to ND trial. This suggests the attention shift toward distraction. And but interestingly, we found only in ADHD group we have this decreased alpha oscillation in no-Go trial, because no-Go trials was used to study the response inhibition. So the finding of decreased alpha oscillation in no-Go D trial may reflect that response inhibition was affected by distraction only in ADHD group. And the second is to examine the between group differences. So we observe that ADHD group has higher ERPS power at different channels and frequencies when compared with the TD group, including those frequencies at different channel. But here we use channels only on our frontal lobe because the constraint of our VR headset. And then it can be seen that distraction additionally enhance the between group differences in alpha and gamma power, which was absent in non-distraction condition. When we compare those two figures, this alpha and gamma only in present only in the distraction trials. So because it was reported that gamma decreases was associated with the inhibition of competing neural networks, so the higher gamma oscillation in ADHD group may indicate insufficient inhibition in different neural network for response inhibition and distraction suppression. Finally, after exam the data with traditional statistical methods, now let's have a look about what we can get from AI. So we try to differentiate the patient from TD, the ADHD from TD. And if we use only ND trial here, we can achieve at most 80% of accuracy. But if we include the trial with distraction, this is actually the traditional way to conduct a go-no-go task, right? And if we include the data with distraction, then we can improve the accuracy to like 5%. This result shows that including distraction data improve classification accuracy. And because we have a variety of different data modalities, so it's also important to make use of them. So here we try a fusion model for classification, and we have the task performance, head eye movement, head rotation, and the EEG data. And you can see that the greatest accuracy can be achieved when use TD task performance data alone or head rotation alone. And regarding EEG accuracy, we can see the greatest one is 70% accuracy from this FP1 channel. But when we make them together, we examine the fusion model, then we implemented two fusion models, the early fusion and the later fusion. So in early fusion, we basically just lump all data together with the proper normalization because their scales are different. And then we can get the result. And for later fusion, we normalize the data as well, but individually. And then we use them individually to train a model. After we get the outcome, the best outcome, we use the last layer weighting as our feature, and then we input them into our fusion model for this classification. And the result is like this. So you can see when we use all of them, we can increase the accuracy a little bit, not too much, just a little bit, to 89%. While the task performance and the head rotation, basically, they are the behavioral data, right? Can give you 83% accuracy as well. And it's reasonable because ADHD is diagnosed with their behavior. So basically, behavior data can speak loud. Oh, so last but not least, we have to see the data. The raw data. In the beginning, we project our head rotation data into two-dimensional space, and then nothing is significant. This is the TD group, and this is ADHD group. If we do a statistic test on the data, we find nothing significant. But then we go back to examine the raw data. We found that actually there is something there. So it's always important. I will suggest that always go back and look at your data before you go further. Like 2 more slides. Okay. So this is the overview of our system. So the subject do the task, we collect the data, the AI do the computing, and finally we can get the result. And the most important thing about our system is that we can make it wearable. So basically we have this, it's easy to use. We may have a mobile app to track the progress, and it's plug and play, and it's compact, and also it can save time because you don't need to go to, you can do this at home, so you don't need to go to the clinic to do this training. And of course, we don't want the subject to feel all alone at home. Nobody is caring them. So we also have this IOMT to make them get connected with the clinician. Also, the upper materials are from those reference papers. And I think we don't have time for the rest of materials, but we have other modalities. For example, this is for substance use disorder, and this is a mobile app to for depression level certification, and this is a system for ADHD. Thank you for your attention.
Thank you so much, CC, for a really nice demonstration of the powerful of using AI methods and in conjunction with psychological data and EEG data for contributing to diagnosis of mental health conditions. Are there questions? Tracy and then Lindsay.
With the diagnosis, are you able to differentiate between different presentations of ADHD or take in gender differences into account?
We are working on that actually because we have different subtypes of ADHD, and we are working on that because at this moment our data are not enough for us to do that, but we are working on that.
And could you go back to the slide where you had the references so I could take a photo?
Sure.
Thank you. Lindsay?
Sorry if I missed. Thank you for the great presentation. Sorry if I missed it. So for the treatment for ADHD, what is the VR classroom like? Is it a very different to the diagnosis?
Yes and no. So in our treatment program, we have different tasks for the subject to do. Like we can use Wisconsin household task to train their working memory, and we also use CPT task to train their attention. But those tasks are all embedded in the virtual classroom. Because it's a kind of to mimic what happened in the real world, the parent and the classroom training.
It's really cool. Oh, and sorry,
Yeah,
another
yeah.
question. For the EEG in the headset, how many channels does it have?
It depends because the headset, the construction of headsets, so we have only limited options for EEG channels, and also we wanted to make it compact. So we for our latest version, we have 4 channels, and from our previous one, we have 7 channels, but they are not 6 channels, but they are not representative at all because they are all in the frontal area. But for the latest version, we have we have 1 here and some other here in the premotor area, cerebromotor motor area, and PD.
That's really cool. Thank you.
Another question? And then that might be the last question before we read.
Thank you. Thank you, Dr. Sun, for a very enlightening talk. Can you tell us about the database? What is the structure of it? Is it decentralized or centralized, or is it accessible to everyone, or is it just for clinician, or what is, yes, those are the examples.
We collect the data, so it's centralized, of course, because we know who and how we get the data. But it's because we are applying USA patent, so we are collecting data at this moment for clinical trial. So it's not public available yet, but it will soon in the future. Yes.
Very exciting. Thank you so much. And again, such a pleasure to have you here. You might find fun fact, CC and I shared, we were at